Good afternoon, everybody. Thank you for coming, and I feel privileged to have a 90-minute slot. I'm Peter Sommerlad, and one big question, because this is the first time again since the lockdown that I speak in front of an audience and not to my camera at home. And who of you have seen a video or a conference talk, either live or in person or in video, from me already before? Okay. Who has read a book or some other thing that I've written before, of those who have not raised their hand? Okay, some few. Okay, maybe I say a few words about me. I'm available via email, and so if you have any questions, don't be shy. I get tons of email, and if they are addressed to me directly and not coming from a mailing list, the chances are high that I'm eager to reply. I'm on the not Twitter thing, but I might occasionally also still use my Twitter account. I have a QR code leading to the GitHub with my slides, and especially for those who look this on video later on, I have prepared a version that includes all my speaker notes, which are not actually notes that I might use during my talk, but notes that explain what's on the slides, especially for those slides that I don't manage to cover in detail. It's things. So, any questions that you might have about me before I actually start? None so far. I encourage you to interrupt me. I might not see it because the light is quite bright, so please make yourself aware that you want to ask a question. But if you have a question, ask it as soon as possible, because it's for me, it would be myself impossible to remember what I said about a slide when I was showing that. So, vulnerable C++. Preparing that talk, I looked up what is vulnerable. It means to be in danger or exposed to. And this is not about the language being exposed to the threat of Rust taking over the world. It's about your code being in danger of not doing the stuff that it should, or actually being in danger of violating security or safety things that it should actually cover. The opposite of being vulnerable is being resilient or immune to or well protected. And most of the time we care about that when I talk about vulnerabilities, about the runtime property, that something happens to your program while it's running and it's not behaving properly. However, most of the things that makes your program not behave properly happened before it actually hit the compiler. And this is what this talk is about. So let's look at what makes code vulnerable. The biggest thing in C++ is that the language has defined undefined behavior. And in the past, it was usually okay, if your program would have undefined behavior by some standard, your compiler might actually do what you expect it to do, and your code run fine. But then the optimizers thought, okay, if this code exposes undefined behavior, and I can prove that this code always will have undefined behavior, I can just optimize away that code that might have undefined behavior and get rid of it, so the program will run faster. It might not do what you expect, but it might do interesting things like drawing unicorns on your screen or whatever you expect to happen. The interesting property people forget often about is that undefined behavior can time travel. So if there's a control flow path that will lead to undefined behavior, not only the code that exposes that undefined behavior can be eliminated, but all the complete path leading to undefined behavior. So even, and that has a bad thing that sometimes you write code to protect against undefined behavior, and if you make a slight mistake in that protection, it actually can lead to that this test code also has undefined behavior, and so everything will fall apart from that thing without you actually recognizing. There are other cases where, let's say, especially if you care about safety critical systems or also security, where there is implementation defined behavior, which is also problematic if the system you're typically testing on or compiling on is different from the target that you operate on, where there might be, let's say, different compiler settings producing different behaviors. And that is also something that should be avoided, especially if you care about a safety critical system. And I won't go into all the details of unspecified behavior, which is also something that has kind of interesting side effects where things are, let's say, defined in the standard to behave properly, but the actual behavior, especially about sequencing, is unspecified so that the compiler can choose, maybe even depending on the phase of the moon, what your code in detail will do. Those are, let's say, more or less the things that are easy to explain. But another thing, we have seen, Miro had this nice talk yesterday with a learning curve that is very long and very steep for C++. And that makes people not understanding exactly what they're trying to achieve. As a former professor, I had students who actually didn't understand what they were trying to achieve in very simple ways, and I had a means of teaching them how to do better. But on the other hand, even experienced programmers might use constructs where they think they do the right thing, but it doesn't, as specified. And that is also misunderstandings about APIs, or just, let's say, typos, ordering of the arguments wrong in a function call. If the types are compatible, C++ will happily implicitly convert everything, and you end up with having the wrong thing going on. Now, what can we do, especially about our misunderstandings? The most important thing is something that I'm doing for 25 years now, more than 25 years now in C++, and this week I learned, okay, C++ people are starting to actually pick up good software engineering practices. I have a background in software engineering. In the 90s, I worked in software engineering research at a big corporation, co-authored a book collecting wisdom of software engineers and software design and software architects. The book is called Pattern-Oriented Software Architecture, a System of Patterns. And I would say today, that still bears fruit because people start to recognize, okay, we have patterns that have been done over and over. We have seen this week a pipeline. So this book contains an architectural pattern called pipes and filters, which is very close to what you can do with standard ranges. This book contains a pattern called model view controller, and there was at least one talk, I think by Victor, who mentioned that for the MFC library. This book contains about the patterns layers, and I think most of you will create layered systems because that's the only means to actually get abstractions somehow right. But most important is something that came out of that. After patterns came, the most people worked on Agile software engineering. Who has heard about Agile software engineering? Who is practicing that? Fewer. The most important thing that came out of Agile software engineering is what I call have guts. And guts is not only what you have in your belly, it's the good unit tests. And this is not a talk about good unit tests, it's a prerequisite. It's something let's say I had to force my students to write. And usually it took a third of the semester standing on their toes to write unit tests. The second third of the semester, they were eagerly writing unit tests for their project work. And the last third of the semester, they were heavily refactoring their code with the safety guarantee of their unit test suite. And they were even brave enough 2 weeks beforehand to do a major restructuring of their code base to get it work. And they will take that to their job later on. And I'm doing that for more than 25 years, and I raised my hand. I don't use the interactive debugger at all. I haven't used one for decades for C++ code. There are some areas where I use debuggers, but that's not what I'm talking about today. But not for C++ code. All my C++ code will have unit tests, and whenever I have a problem with understanding what the code should do is not what I think it should do, I write a unit test to expose that thing. And if you want to learn more about that, I have a link in the handouts for Kevin and Henny, and there are plenty of talk. And if you want to learn more about that, reach out to me if I can give you more resources. So have guts. What does it mean to have vulnerable C++? There are a few things. There are things that are immediate. You have undefined behavior in your code and the compiler can prove it. The other thing that is also vulnerable is if your program isn't doing what it's supposed to do because you made a bug. Not even, both can come from misunderstandings, not knowing all the details, which is impossible for C++, by the way. There are other things that are kind of lurking undefined lurking vulnerabilities where there is data dependent, either undefined behavior or misbehavior that only happens under special cases. Example would be division by 0. If you never get an input that leads to divisible 0, everything is fine. But if something happens and that gets, you try to divide by 0, that's again undefined behavior. Another thing, software lives and we change software. And especially when you have guts, change is actually easy. But what can happen is that the code is incomplete, that people who change the software don't have the guts of the previous people, or that previous people didn't write unit tests or not good unit tests, and you change something without understanding it completely. That can lead to, again, incompleteness, confusion, and not behaving properly. And another thing that's about the implementation-defined behavior is the portability of the effect, especially when on new hardware. And I'm old enough, unfortunately, that I have experienced the portability from 8 to 16 bits, from 16 to 32 bits, and now everything gets to 64 bits. And I think most INTs are still 32 bits, even though our processors are better with 64 bits now. Just because, yeah, maybe the code is not behaving properly if we change that to make it too big. Now, just to get something to take you home if you don't want to stay all the talk, these are the most important, in my opinion, when I wrote that slide, resilience mechanism in C++. First, the good thing about C++, it has an ISO standard. And if your compiler doesn't conform, kick your vendor. And there are some commercial compilers that need a little bit more kicking. Others might ask you, yeah, please provide a patch because we are open source. But nevertheless, there is a standard. And actually, vendors are trying hard, let's say from the major compiler vendors, to actually be conformant with the standard. Being on the committee, I see the discussion of the people on the so-called core mailing list where, okay, how do we interpret that sentence in the standard, or maybe even that comma in the standard, to see how things are implemented, but they are eager to get conformant implementation. And if you want actually to be your program to be portable, especially across compilers, not only use multiple compilers, but also set the compiler flags in a way where violations of the standard are errors. And this is also important. Let's say, for example, GCC has a long history of providing extra features that are not part of the standard, which might actually have been picked up by Clang as well, just to make the code compile. But this doesn't mean your code is portable. And it's also the other way around. If you program something with on Windows with Microsoft compilers, then you might end up with code that doesn't compile happily with all the other compilers, or at least not standard conformant. Another good thing about the language itself, and that's why I'm still such a big fan after 35 years of C++, C++ has a very strong type system. And also a good library to use, especially important, the algorithms library. Algorithms help you to avoid the typical common bug writing a loop with a one-off error or just a wrong loop. There are no loop conditions when you just call a function. You might need to have the proper arguments, but that's a different story. That's always a thing. Now, another thing that makes C++ very powerful is the next two bullets. It's about the deterministic object lifetime. The standard defines exactly when an object starts to exist and when it ceases to exist. And in both cases, we can run specific code that happens at those specific points in time, especially the curly brace, closing curly brace of a local scope will destroy all existing objects in that scope. And this destruction, this deterministic destruction, so the curly closing brace is one of the most important things that you should embrace in your code bases. Compilers have become very, very good in detecting your bugs and treat them serious. Turn all compiler warnings as error. There might be extreme cases, I have those in libraries that I write, where I deliberately turn off a warning in a specific case because I would say the compilers are too eager to warn me that it's wrong and I can prove it's right what I wrote. And that is sometimes the case, but I would never dare to turn off warnings as errors in my code that I try to write. And I'm not sure if Matt is still here. It would be great if Compiler Explorer would have turned on W error for every compiler by default. And in addition to the compiler that is a good static analysis tool, try to use others as well, like the address sanitizer, undefined behavior sanitizer as dynamic tooling, and there are other static analyzers, free and commercial, and some of the commercials one are actually cheap. You don't have to go to the big vendors where you have where the salespeople only speak with multi-billion-dollar CEO companies or maybe purchase departments. There are things that are actually cheap that even a private let's say a freelancer can actually afford to pay for. And also avoid the bad stuff. Now, what's the bad stuff? That's the main topic of this talk. A little bit of my history. I do a lot of voluntary work for the C++ Standardization Committee, for committees that create guidelines for C++. I cooperated with the automotive industry for free on the AUTOSAR adaptive C++ guidelines that address C++14. I collaborate closely with other people on the upcoming MISRA-C++ guidelines, where the technical work was just finished last week. So stay tuned for them. If you ever have used MISRA-C++ 2008, know the new guidelines allow you to write much more modern code and much more C++ code. And they might give you some issues if you write very classical C++, because that's what we are trying to get away. And also, last but not least, I work for the ISO IEC JTC1 SC22 WG23. You might have heard people talking about WG21, which is a C++ standardization committee, and WG23 is about programming language vulnerabilities and their avoidance. And it has a series of standards, some upcoming, some published and republished. So the most important, or let's say the entry point to the series of standards is the -1 standard. So it's 24772-1, and that's the language independent catalog of the vulnerabilities. There are further standards for Ada, C, Python, Fortran, and C++. And to get, let's see if I can make that work. There is an online version of the C++ document, and this is live, more or less. This is generated automatically from the repository where we do all the edits. So they are still completely incomplete, still buggy. The link is in the handouts, and otherwise you can find it. It's on, everything is on GitHub. The actual editing happens in a private repository, but all the HTML is generated and can be viewed freely on that page. Now let's see if I can go back. The language-independent document has a structure with 6 subsections, and I use that structure to explain, give one example of those things. And a lot of the rules are, let's say, based on features that are, let's say, problematic across these languages, but there are, let's say, many of those you will see, oh yeah, that's a problem in C, and therefore also in C++. So each rule has a description of the vulnerability and refers to coding guidelines that tell don't do it like that. And it explains what can go wrong. It explains what language characteristics in general are required. So for example, a language that wouldn't have any pointers and pointer arithmetic wouldn't be vulnerable to pointer arithmetic errors. And there's the avoidance mechanisms that might be in general, and also avoidance mechanisms where languages can actually change to become better in that respect. And if you look at some of the avoidance mechanisms that are, let's say, relevant for, or where C is not avoiding the thing, you might actually find that C++ got away of that by the language definition, or at least by providing features that make it easier to mitigate. Now, one big thing that can go wrong is the pointer arithmetic. Each of the guidelines of the vulnerabilities has a 3-letter code. Sometimes they look like airline codes. Sometimes they are initials of favorite persons. I haven't figured out each of them where it comes from, but pointer arithmetic is something that can go wrong, and I wouldn't read all of those details, but anybody who has used pointer arithmetic knows, okay, things can go wrong. I might access memory that's not belonging to the program, which is good. Then most operating systems would just kill my process. But if you're an embedded system without an OS, you just get arbitrary data that you might read or write to, which is also something that can be problematic. And what you can work on, you can try to avoid pointer arithmetic, and the general guideline tells, okay, use indexing. We all know in C and C++ indexing is pointer arithmetic, so there's no win by using indexing, especially since indexing in general is not protected against out-of-bounds access. And the last thing is, okay, limit pointer arithmetic. Yeah, good. And that is something I'd like you to do. Now, there are 64 vulnerabilities. I wouldn't go into all of them, just to give you an impression. We have things about the type system, about representations, about all kind of buffer and pointer things that can go wrong, about, let's say, naming, which is mostly the thing of getting good at not having the confusion things. Unused stuff is typically a problem. Namespace issues is something where C++ has very specific rules about, let's say, argument-dependent lookup, and let's say things like hidden friends can help you with that. And there are other things like off-by-one errors, which is also something classical, unstructured programming, and their EWD is actually the initials of Edgar Dijkstra. So that's one of the codes that I actually know where it comes from. And there are more and more and more. And if you look, I said 64 vulnerabilities, and we end up at 65. This is not an off-by-one error, which is one of the vulnerabilities, because the .1 is actually an introductory chapter. Now, what are there's in the -1 document, there's also kind of the top avoidance mechanism that have the most rules would benefit from if you use that. One thing is check your inputs and check the error returns. And that is very closely related what people are calling contracts, so the precondition and the postcondition checks. Also, what I already said, enable compiler warnings and static analysis tools, and perform range checking, which is something that is tedious in C++. I have some ideas to actually make it able to retrofit range checking, but I have no clue if something like that would pass the committee. So, but I have a list of papers to write for the next meeting, and I will try something. And the fifth thing is something that is, for the general part, allocate and release resources at the same level of abstraction. And this is actually something where C++ shines with this scope-based resource management, when you create manager classes to make your code work better. Now, one example from the C++ list to just give you a thing. One vulnerability that is in general is 6.7 is string termination. And the general case explains the situation as it is in C. And if you look at C++, okay, we have that convention of the null termination inherited from C. And it can cause buffer overflows if there's no null when you walk a string or misallocated space and all kind of bad things that can happen. However, in C++, we have a cure that actually avoids all of that. Use standard string, full stop. String view and span don't help you with that, but standard string, if you exclusively use standard string for your string handling, you have no need to scratch your head about null termination of anything. And I hope you're not using functions starting with str from the header C string in your code. Any confessions? Okay. So for example, MISRA forbids using these, MISRA-C++ will forbid using these functions. I didn't hear that. Can you use the microphone? I'm hearing impaired. Say?
He says, what's wrong with string view?
It doesn't guarantee null termination. So for this thing, it doesn't work. String view is not having null termination. If you produce a string view as from within a string object or wherever, it isn't null terminated. If you then pass the, let's say, the beginning of that string view to a C function that expects null termination, you're getting that vulnerability. That's wrong with string view. There are many more things wrong with string view. It's a good thing to have, but not for null termination. That doesn't solve it. My general advice, if you look at directly at C++ resilience, is use value types. There's something that I call relation types that the vulnerabilities document currently calls pointer-like types. Everything that refers to another object that might go away or might change its state that's no longer available. Create application-specific strong types. Björn Fahler has a talk on that, and other people have mentioned that. If you want to learn more about that, there are talks by me and others on how to use strong types, and even a library that I created and others created other libraries. So you can have even the option to choose from different libraries to make your own strong types. If you look at one of my talks on that, you will see you can even DIY without much hassle. Just wrap your type in a struct instead of using, let's say, int, for example. A thing that I might elaborate a little bit more on later is conscious error handling. Error handling is something we're bad at. It often comes as an afterthought. And this is why a lot of the guidelines tell you do error handling. Also, no loops. I gave my students the usually exercises, use no loops, use at most one loop, or use at most two loops if it was a little bit more complicated problem. Most, let's say, some of the students, even with the two loops exercise allowed, handed in solutions without any loops. So it's possible. It's not always, let's say, the most obvious solution, but I would say most of the legacy loops are not what you want to write. A non-range-based for loop has a very rare situation that you actually need that. Me and some others tried to pass that through the MISRA guidelines to no legacy loops. We failed because the feedback was overwhelmingly bad. We still have the opinion it would be good to the target audience, but they weren't ready yet. It's many things that I was preaching for, let's say, sometimes decades. Like, for example, in the 1980s, still a university student, I was teaching C for a training company. And then when you had one guideline that I taught was, oh, if you have a function that takes more than 3 parameters, wrap those in a struct. I don't know, Vincent is here. He had that exact example. Okay, you have many parameters, wrap them in the struct. And now in C++20, we also have designated initializers that helps us to make that even more interesting and interesting features. But having functions with too many parameters is an indication that first, the function might do too much. Remember I said with Ben's talk, 5 lines is a long function. And that the abstraction, sorry, I should have, yeah, it's not Keynote running, it's the browser that therefore it turns off the battery turns off the screen, but you have to shout and then I can just wiggle. Okay, where was I? The long function, yeah, 5 lines. So either the function is doing too much or the parameters typically belong together and should actually be encapsulated. Example from the C++ library, algorithms, they always take iterators in pair. Now we have ranges where we have a range, which is actually pairing those iterators, modulo some extra features. And this is something where parameter type, too many parameters is something that, okay, that was 35 years ago or something. It's still valid advice. Cool, that's cool. Also, we have our curly brace deterministic object lifetime, the consequent use and design of manager types. I have a talk called What Classes We Design and How, which goes very deeply in how to create managers and what to do with special member functions. The major rule is write your code that you don't need. Rule of 0. Core guidelines everywhere. Rule of 0 is the key thing, but in some places you actually need to manage a resource, and that is where you write your manager in a conscious way. And a lot of classic code has bad things in there. Refactor. Anybody has written a destructor with an empty body? Confess. Go home, delete them. They do nothing good for you except creating too much source code. Treat, I already said that, and the bad stuff I don't need to repeat. Now, I have these bold things. There's a sidetrack that I want to mention a little bit. Use value types. Be aware of relation types that point somewhere else. They can dangle, and that might go bang with your program. We have that strange polymorphic types using virtual. Be careful with those as well. I have another talk that I gave last week. The C parts and the OO parts in C++ actually the dark corners of C++. The rest is much more shiny than that. So whenever you see virtual, think there might be better replacements, especially if the set of subclasses is limited. Don't do deep hierarchies. I had a fight. Why do you do a 3-level hierarchy? 2 is enough if you really need inheritance. If you use templates, you might not even need inheritance. Just implement the same concepts in different types and use them as template arguments, and how to do manager types. And I will skip a little bit over some of these things that I don't want to address in detail and look for that I promised you about precondition checks and error handling. These are the top 2 mitigations we have seen. And there is this thing about, oh, what's a function contract? That's also something from the 80s. Bertrand Meyer and maybe some others in his vicinity came up with that, and also Dijkstra-Hoor worked in that area. The thing is, what is a precondition? It's something what you as a user of another function has to ensure when you call that function. And sometimes it also means something that the function can actually check. There are problems with some preconditions because there are preconditions that nobody can actually check, or at least not check in a way that makes your program still compute reasonably fast or at all. On the other hand, if a function creates a result, there are postconditions what the result will actually conform to. And I will explain a little bit, or maybe say it now. Postcondition of a function usually means that a function has a side effect. either because it's doing I/O or because some other state that is outside of that function is actually changed. Your member variable might be in a specific state after you call that function. For example, if you use vector reserve, you know that the amount of elements that you pass as an argument to reserve is available without further allocations. And that is something, a postcondition guarantees something that is usually outside of the actual function realm. So I would say any void function will have postconditions that you should be aware of. Otherwise, don't call it. Now, some terminology from fault tolerance. A fault is actually when either a precondition is violated by the caller or a postcondition cannot be satisfied. Something went wrong. That doesn't mean a lot. Only when you can actually detect the fault, it becomes an error that you can handle. Now, what can we do in C++ with errors? You can ignore the fault and just maybe have undefined behavior. This is the approach that is the fastest runtime and very often used in the C and the C++ library, because the libraries expect you to be the superhero programmer that always has the responsibility and the ability to actually make no mistakes, which is, let's say, an interesting approach. It was a very valid approach when Ken Thompson and Dennis Ritchie invented C for themselves and their direct peers, who were actually the superhero programmers of the early 70s or late 60s. But today, so many people are more people are programming, that it averages out. The larger a group becomes, it's more average. Even though C++ people tend to be superhero programmers, we are not perfect. The next option is to return a standard result to cover up the error, which is also sometimes important if you want a system that continues to execute. It's not a very common one, and I don't want to give too many examples about that, but sometimes functions just return 0 if you cannot produce a useful result, if you can continue to compute with 0. The next thing is something that is important when you don't want to use exceptions: return a special arrow value. In C++23, we have standard expected, we have standard optional for that. Sometimes you have a domain of the result type of a function that has some extra spare values, like POSIX often uses -1 to denote, oh, something went wrong. And you're not supposed to use -1 as one of the handles that POSIX API is using. Another thing that I don't recommend to do is provide the error status as a side effect. Side effects are evil, and the most evil thing that we lived through with is Erno. There are other evil things that are in the range towards the standard result. If you use a standard iStream, if some input fails to actually be correct, the stream goes into a fail state, or maybe if the input is ended to the AOF state, and that's a side effect you have to check and nobody asks you to check, and the stream will happily continue to operate just doing nothing when in that state. And last but not least, you can throw an exception, but for all of these things, at least for the 1, 2, 3, 4, you need to be able to detect the fault. And some faults you are actually not able to detect. For example, if you want to sort a range, you provide a predicate. And there are some things that the predicate must fulfill to actually sort to work. If you provide a predicate that doesn't work like that, sort will fail with undefined behavior. Or standard set of double. Who has ever created a standard set of floating point numbers? Not even in an exercise? Oh, one, a few. Be aware, once you get another number in that set, your set precondition of comparison is violated and you will never get another number into that set. Unless you use a special comparison functor, which is not the default for floating point numbers. So be aware. Not a number is not a friendly entry into a set of double. Another option is never fail. There are some functions that never fail. One that is guaranteed to always succeed is the identity function. And you might even see a generic code example that have to use identity function to actually get something done to make sure, for example, prevent template argument deduction or something like that. And there are functions that always succeed, and that is something you could go for. And I will click a little bit quicker to the other things that I don't want to go into and explain a little bit about, okay, if you have a function with external dependencies, and typically that means you interact with the runtime or the operating system or on an embedded device with the hardware, where you do things like memory allocation, I/O, other resource allocation. You might have to create handles or threads, or whatever. And those things can fail for reasons that are beyond your program's control. And those actually can lead to a postcondition violation. A function, you want to open a file, the file is not there, the file stream will tell you, I'm not open. You need to check. And it cannot do that. So what's a failure mode? A system or a human must work on that. Either your system is fault tolerant and cares about, okay, I couldn't open the file, I do something else, change the file name, increase the file name, or try a different directory to store the stuff that I know it's writable. Or it's the human to tell you, oh, you entered a file name that is invalid for your operating system, please provide a different file name. And there's a nice talk by Herb Sutter where he explains about all these kind of bad things that can happen and categorize in three levels. One is the undefined behavior level, where the only thing when the so-called abstract machine is broken, when you have had undefined behavior, is actually terminate the program. Throwing from a no-except function will terminate a program, but there are other situations where the best thing that could happen is actually terminate the program, because otherwise you might, in a safety-critical environment, kill people. But that means that someone actually needs to handle that. So in C++, when you write safety-critical system, there always needs to be an extra level to handle that. For a self-driving car, or let's say an airplane, where it's more common, if the autopilot fails, there are usually one or two humans there to actually deal with that failure and fly the plane by hand. That's important. If your brakes fail on your car, usually you have two circuits for the hydraulics to actually still be able to brake somehow. If it's a programmer bug or a precondition violation, so the programmer made an error, that is something you can actually assert, have otherwise checks, throw exceptions. And this is actually things the programmer needs to know about and fix. And the typical fix is write better unit tests, so have guts. And it's a human that has to deal with that. And there are other things that I explained. The recoverable errors of postconditions cannot be guaranteed. That is where you write code for fault tolerance, if that's an issue. And if you care about safety and security, fault tolerance is an issue. And if you want to make money from, let's say, selling online stuff or phone calls or whatever, fault tolerance is also an important aspect. Now, which strategy of these 5 or 6 is actually the best one? It depends. The important thing is that you have a conscious strategy, and sometimes it's also important to have different things, do different things than have just one. For example, in Java, we used to have everything, all error messages, all error handling in the beginning were with exceptions. And you had to specify which exception might be thrown. IDEs were created to actually automate the specification, but most of the systems ended up with the exception hierarchy derived from runtime exception, where you didn't have to specify which exception will be thrown. And so just having one hammer might lead to too many nails in your way. You might want to use different strategies. And important, with the strategy, also unit test the error situations. Don't forget, have guts. Now, that's preaching.
Question?
Yeah.
Do you
if the function is supposed to test for the precondition violation, I write tests that violate the precondition and see if the error is actually recognized and handled. So for example, if you have a function that expects a non-null pointer and tells you, oh, in the documentation, please provide a non-null pointer, I call it with a null pointer to see what happens. And I expect the outcome. Unless it's one of those 0 level, ignore any precondition violations, which is, let's say, in safety critical code, not recommended. We have these relation types, and a lot of things you can actually mitigate with a C++ type system. But once you end up with something that is pointer-like, and that means you have an object or a value, well, references are not objects, but for the moment, let's say objects, you have an object that relies on the existence and the validity of another object. That is when you end up with a relation type. And those are the ones where we actually need to pull on our goggles and cape and be the superhero to track that these stay valid. And it's not only pointers in C++, which I say you shouldn't use at all except tightly encapsulated. It's also references, iterators, ranges, not ranges, views, string views, bands, or even standard reference wrapper, which is something you might not know about, you might not want to use it, but unfortunately the standard library optional doesn't allow references, but you can create a standard optional reference wrapper, which I have been doing to avoid having a plain pointer instead. Now, if we look, there's a whole list of things that all relate to, let's say, pointer things, and the most important things for me to deal with is dangling, because again, a lot of things you have there can be easily avoided by using the appropriate types, the appropriate structures, like a range loop or like an algorithm. But dangling is something that you cannot easily avoid. And there are two actually vulnerabilities in general. One is dangling reference to heap and dangling references to stack frame. And I, again, would like to navigate a little bit further on to jump over stuff, which I'm not sure I can do there. Maybe just what can I do with these dangs or these relation types or pointer-like things? Passing them using them as a function parameter type is usually okay, because the actual reference goes to a scope that is always existing while the function works. Some people even call things like span a parameter type, because that's the one place where actually the superhero can relax a little bit, because if the caller doesn't make a mistake, you can just within the function refer to something and it works. If you have globals, you can access them. They will never dangle if they are global variables, but they make the code very hard to test, sometimes even untestable, and that's not a situation you want to enter. So if you have mutable global variables, refactor away from them. One thing is parameterize from above, pass them as parameters to the function that are using them. Bendine even showed us a trick how to do it without having the explicit dependency and only an implicit dependency that you can actually change for tests. I still haven't got my head around if that's the brightest idea since slice spread. Better, in my opinion, it's still better to pass things as parameters so that you can actually have the dependencies that your functions rely on are transparent. Don't return relations. That's mostly the dangling reference to stack frames. People have tried that, and the code might seem to work in C, for example, or at least on classic C systems, because the bits on the stack are still the same when the caller gets that pointer that refers to a local variable that was created in a previously called function. But that's danger happens. It's undefined behavior and boom. So don't do that. If you have a parameter and you return something that comes from that parameter, and for example, all containers use these kind of accessors like returning an iterator or returning a reference from, let's say, vector front, for example, will return a reference to the implicit this object of the vector that points with or refers to something within. That can be okay as long as this returned pointer-like thing doesn't leave the current expression, because it might actually refer to a temporary object and you end up with a dangling. So it can work, but be aware there is danger lurking. If you have multiple threads passing relationships from one thread to the other, boom. Unless it's a completely const thing, don't do that. You get either you need locking, or you need get data races or lifetime issues because one thread is finished and this local object is gone. Don't do that. But people try, and the compiler wouldn't help you with that. Globals and threads, okay, they might not dangle, but again, you get the data races unless you put all the globals. Let's see if I can point that out. Oops. Oh, I'm not getting there. Unless you put all the globals, oops, with mutexes, atomics, or whatever, that they are protected. So also, not a good idea. If you really want, I said that, use atomics or mutexes, but be aware, using those things creates a lot of overhead. If you have your 32-core super high-speed machine and then you access a mutex or an atomic, that means all 32 cores need to synchronize the caches, need to more or less stop. It's like a 64-way stop where everybody has to stop before anybody can go on. Be aware of that. Now let's look at the specific things that are said about C++ on dangling references to heap, and I have no idea what XY is. Maybe it's an airport court. But it's a stable name like the stable names in the C++ standard, if you have ever seen that. So the difference from, let's say, the general document on dangling references to heap with C++ is the lifetime model of C++. The general document assumes once you have a pointer to the heap, the pointer and the accessing the memory is okay. In C++, no. There must actually be an object living at that memory location. We have that deterministic object lifetime model, and there must be an object. It's not just having casting a void pointer to something else and assume that you can access an object like that. There might not be an object there. There are some changes recently on allowing more things that compilers make to work anyway, because even if it's undefined behavior, they provide you with something. So it's less undefined behavior now. But again, what are the typical issues? Double releases. Whoever gets a double delete on a pointer in C++ should actually hand in their C++ driver's license and go to re-education. There is no need to actually call delete or similar free on any pointer in modern C++ yourself. Another thing is dangling, access memory after release. That is a problem. That is where you need your superhero and programming skills to make it correctly. And memory corruption usually means you have dangling or out of bounds accesses. I don't go into that details. One area that is not so obvious in C++, if you have iterators to containers and we keep those iterators around, maybe because they were returned by a find if, we might end up with a situation where the iterator is invalidated. And that's a danger that is not, let's say, easily obvious, for example, for beginners, especially not for those who have programmed with Java, where actually an invalidated iterator might be recognized by the runtime, and there's infrastructure doing so. C++ iterators are optimized for speed, and like views and iterators might dangle, so be aware of that. Now, what can we actually do to avoid, well, don't allocate and release yourself. Use manager types, string, vector, your go-to types. If you really need to use your own, create your own node-based data structures, use make unique. There are other things about allocation and reallocation. Other managers like scope, block, and fstream are things that you might want to go to. Again, what are the avoidance mechanisms? Vector, make unique. There is no new and no delete in any pieces of your code when you go home. And if you have new and delete in your code bases, eliminate them. Use value types or use make unique. No calls to destructors. Not even destroy at, unless you're really the Ken Thompson level expert, super expert, C++ expert library programmer who creates their own, let's say, generic container types, which is a rare need. I teach that to the experts level course, but only to show them how things like vector might have been implemented. And also sanitize your addresses. And for all of these 4 first bullets, go home and refactor your code. Now, dangling references to stack. Those can be very interesting. There are even code that looks completely, let's see if I can manage to show that. Just calling max. It's a function from the standard library. It shouldn't have a bug. Well, this is actually a potentially dangling piece of code. And the key is I take the literal return type of standard max and memorize what the result was. Well, I want to save the copy, so I bind the reference to it. The problem is if I call max with a value of I that is less than 20, the literal 20 will be a temporary on the call stack of max, and you will get a reference to that temporary, and there is this deterministic lifetime. All temporaries are destroyed when you actually end at the end of the statement. The semicolon is the end of the full expression that you have here for initializing that or binding that reference, and that means you end up with something referring to a local temporary object that has been destroyed when you actually use it. So even when you create the new return value by returning m by value, it's an int return, even then you access a dangling reference. Fortunately, compilers aren't too bad in detecting those, but in general, I would ask you to never ever use local references you bind stuff against. Use a local variable. Compilers are very good at micro-optimizations, much, much better than all programmers in this room or at this conference, or maybe in Toronto, Canada, North America combined. Don't micro-optimize and don't do things like that. The standard is guilty of such a micro-optimization. The range for loop has a subtle potential hole that can be exploited, and only C++23 fixed that. And it was a heavy and long discussion. It took Nikos Youssoudis years to get that fixed. Other peculiarities. We have that feature of a reference lifetime extension. When you look at the design and evolution of C++ book by Bjarne Strustrup, where he explains the early decades of C++ and how it was created, it was a compromise that const reference bind to temporaries and make the temporary lifetime extended towards the end of the scope of that reference. And the rules are really tricky. For example, if you use it to actually bind to a member variable of a class, the reference will actually extend the lifetime of that temporary. A42 creates a temporary object of type A. .A actually accesses the member of that class, and binding that reference actually extends the temporary A of capital A towards the end of the scope. If you refactor your code and use getA, which is just a function returning the reference, there is no longer any lifetime extension, so the const reference A, CRA, is actually dangling immediately. That's one of the big dangers, and that is something that happened, was the problem with the range for loop. And actually, with all the copy elision that we get, there is really, really a rare case where you might benefit from reference binding. There might be a performance benefit, yes. The only time you should actually change your code to get better performance is when you can measure that it makes a difference. And many people never measure and believe they write optimal code. Remember, the compilers are much better at micro-optimizations than you are. And you might even pessimize your code because the compiler can no longer micro-optimize it when you try to do it by hand. Don't. Simple code. By the way, something I talked about 15 years ago at another conference as a workshop. Simple code is important. Now, there are more interesting pieces of dangling to the stack that you can produce. Return a pointer to a local bad pointer. That is something that's detected by the compilers. Or returning a reference to a parameter. Easy to write, easy to do wrong, and it's just not working properly. But there are more interesting parts. You might have a local variable that is an array and you return a pointer to that. Well, maybe you had that array being static and just got rid of the static and the code no longer works. And this is a kind of dangling that is not as obvious, so the compilers might not be able to check that. Or you return a lambda from a function that actually has a capture by reference, also dangling. Or that's even, let's say, shows us the problems of doing things where the built-in assignment operators can actually assign into a temporary. Nobody is doing that, but it's technically possible. So we create a temporary string object, default initialized, assign to it another string object, and return with deckel type auto, not by value, but by reference. So we return an L value reference, which is actually the return type of an assignment operator, to that temporary object that we just assigned into, which is actually destroyed at the end of the expression, which is a semicolon. So this is immediate dangling. And let me check if I can actually switch to the corresponding tab and go bold. So this is the code that we actually have seen. Bad pointer, bad reference, bad array, bad lambda. And if we look closely, we get warnings by the compiler, and see, I didn't turn off the warnings, so we get warnings about the return the pointer, we get warnings about returning a reference, and we get that even twice, I don't know why. But all the other things, we didn't get warnings. We just get address sanitizers, errors that something went wrong, so we get a segmentation violation because we had an out-of-bounds access of our memory area. So it's very easy to write code that compiles perfectly. Only the very obvious cases are warned about, and many others can silently be hidden, and the compiler wouldn't be able to tell us. even more bad things that are subtle. Something I didn't even think of when I saw the example first time. You have a member that is a reference, or maybe even reference wrapper because you want to have assignment, and then you accidentally initialize it or bind it in the constructor to refer to a parameter variable, which is a very subtle bug. Fortunately, it is detected by the compiler, so not that bad, but it's something easily overseen in review because, so don't use references, but sometimes you need to, so that's a bad thing about that. Also, a very subtle thing that comes from implicit conversions is something that is not that easy to see. Here we have a string view that we initialize from a string literal. Oh no, there is a literal suffix called s. What actually happens, instead of having the literal string which stays in memory, someone was clever enough and say, okay, we don't use literal strings, we always use strings objects, because I said so. And we end up with a temporary object that is actually gone at the end of the semicolon, where we bind a string view to that is dangling immediately. And this is a very subtle bug to get a dangling string view. So string view is good as a parameter type, very bad as a local variable type, because it might just immediately dangle. And the last box on that slide is the demonstrating the dangling that the range for loop has. If you have a nested container and create a temporary container and look into the first element of that container, which is again a container, here a string, and that would actually immediately dangle because it's a function call or not a member access, a data member access, so we get immediate dangling, and it's not, it might be recognized, and it's only non-dangling from C++23 on. I'm not sure, I haven't checked if it's a backward compatible, a backward change, so that compilers will also compile your, very modern compilers will also compile your code, not misbehaving, but that's something to look out for. The MISRA guidelines, for example, will tell you if you use a range for loop, only have a single function call on the range expression and not more than not two function calls, to avoid getting something that might dangle. The thing that I already showed you is the problem with the assignment operator. If you have a default class where you get the default assignment operators, you can assign a temporary and return a reference to that, and that will compile. To get rid of that, whenever you define your own assignment operators, to make them L value ref qualified, that extra ampersand here ensures that this function can only be called on an L value object, a variable, and not a temporary, which would be an R value object. Now, unfortunately, when the feature of having ref qualified member functions was designed in the beginning of the 2000s, it was suggested that the built-in or compiler-provided assignment operators would actually provide these ref qualification. It got forgotten in the hype about the first version of concepts and getting C++ OX before 2010. It just got forgotten. Nobody proposed the actual change to happen. And this is something I wouldn't tell you to create all assignment operators like that, even if the compiler provided would just work. I might actually write a paper proposing that, but I think that's too late because code might actually do something like that, ridiculously, but nevertheless. So I will, just if you create your own manager class, where you need to implement assignment yourself because you're managing a resource, that is when you actually should create the assignment operator with an L value ref qualification to avoid having it called with the temporary.
Would it not be the same to delete the assignment operator that takes an R value reference?
if you delete the assignment operator, any assignment operator,
Delete the one, the R value reference qualified assignment operator.
then you wouldn't get the compiler provided one at all and you wouldn't be able to assign. It's a complicated rule set. Look for my other talk about what special member functions you get when, and it's not easily mitigated.
Assignment to an R value is being used in proxy classes. So if you are implementing a proxy class, you may need assignment to an R value. We can proxy uses an R value as a local part that was created in the function, and then you do need the assignment to an R value. So in some cases you do need it.
There is someone commenting about R-value proxy objects, and I didn't get my head around what you were saying. I'm sorry, I cannot answer that right now. Just write simple code. Don't try to fix the language. Just make your code a little bit well-behaved. And if you look at that 633 rule in the C++ document that I showed you on GitHub, or the GitHub pages, you will be able to see all the mitigations that we actually propose that you should do to your own code to avoid those dangling things. Now we're running out of time, but I still want to show you some other things that are problematic with the built-in with the language. We have a lot of things talking about built-in types. It's only these sticks that I picked out. So kind of floating point arithmetic. If you're not an expert in numerics programming, don't do floating point arithmetic unless you don't care about the accuracy of any of the results that you produce. But we have the type system and implicit conversions, and those give us a lot of problems. Whenever you design your own types, don't make the mistake of the built-in types, and many of the standard or some of the standard library types don't have implicit conversions. String view and string are guilty. We've seen an example where you get dangling, immediate dangling because of implicit conversion from string to string view. Arithmetic wraparound errors is something, if you have signed integer arithmetic, wrapping around might just happen, but it's undefined behavior. I deliberately created a library to provide replacement integers that always wrap around without undefined behavior, even the signed ones, and that don't implicitly convert among each other, which is also an important property. Who knows all the rules of the usual arithmetic conversions on the top of your head? Who has heard that there exists something that's the usual arithmetic conversions? Okay, that's not half of the people here. And you all have used integers, I guess. Just a simple example. What type does this expression have and what's the value? Who was raising hand about usual arithmetic conversions? What's a type? That should be easy. The type is unsigned on a 32-bit machine, and it's always unsigned. But the value is something very hard to guess because it's quite big. A naive math person would say, well, that's minus 84, isn't it? It isn't, unfortunately. Also, bad thing is about bool. Things convert to bool, which is actually great for a lot of things, especially explicit operator bool types, like a unique pointer. Sometimes you get silent narrowing, silent data loss. Changing the signedness is the bad thing about integral promotion. I have no clue why this came into the standard. In the very early Koenig and Ritchie C I was teaching in the mid-80s, it didn't happen. But then we had 16 bits only, so. And the wrapping of unsigned integer arithmetic is, by some people, also considered harmful because you have no means to detect that. You have an overflow. There are libraries out there that deal with that. And another thing that the built-in types are very badly characters and strings. What about Unicode? Kate asked that. Björn told us, well, character is an integer, and it is even more than an integer. We get promotion rules. It has a special meaning if it's pointer to a character or an array of characters, because that can be just memory, it's bytes. We have standard byte, but backward compatibility will keep that around. Now, what can we do about the type system? Use strong types, distinct types for your own application domain. If you want to learn more, watch one of the videos. I have one from CPP now, C++ now, CPP, C++ now in 2021, which is where I speak only to the camera for an hour or so, which was less nice than being here. Enforce type compatibility and take every cast that happens either explicitly or implicitly by the compiler as a potential bug in your code, because you have a type mismatch. Respect unit systems. Sometimes you have to invent your own with strong types. Sometimes you might be able to reuse a existing unit system for SI units like those of Matthias Busch. But be aware, sometimes your domain units might sound like physical units, but aren't. For example, to compute, in Germany we have, or in Central Europe, instead of miles per gallon, we have liters for 100 kilometers. Liter is a volume, kilometer is a distance. If you divide a volume by distance, you get an area. So what is your car with 10 square kilometers area doing? You don't know. So be aware, it's not always physical units, even if they sound like that. Bit representation, actually this is where the general document on that rule gives us something that tells us, oh, use bit fields. And the C++ guidelines tell you, don't use bit fields. Why? Because you have no control by the standard, no guaranteed control how the layout is when you use bit fields. You have increasing addresses, but you don't know about silent padding the compiler provides and anything. If you really want to talk to hardware, DIY bit access or use a library, there's one by me that provides you the ability to specify bit fields, and it's the only case where I actually use union deliberately without making, where I think it's not having undefined behavior. Because it's very easy to have undefined behavior with unions. And I've seen at a client their use of union for that, and their use had undefined behavior. That was my motivation to write a library where it doesn't have undefined behavior. It might change, I'm not sure if the rules have changed already in C++23 to give a little bit more leeway with type hunting with unions, but what you do in C with type hunting and unions is undefined behavior in C++, except for very rare special cases, which I make use of in that bit field library by me. Conversion errors. This piece of code is a pink background, so it's bad code. Who knows what this code has? Does it have a problem? What's the problem? Just multiplying two unsigned shorts with a very specific value. Any? What's that? There is an overflow, and that's just the square root of the 2 billion somethings. There is an arithmetic overflow. What happens? We have, when we use an unsigned short in an expression on a 32-bit machine, it gets implicitly promoted to signed integers. Why? Because the standard says so. Multiplying two signed integers is subject to undefined behavior on arithmetic overflow. And this is the first value. If you use 46,340, that is just not overflowing if you square it, but otherwise it overflows. So you can play around. In the handout, there's a Godbolt link that actually exposes that, and you will see that if you use the undefined behavior sanitizer, this is a case that it actually catches at runtime. What can we do about conversion errors? Don't use casts, don't use type punning. If you're a C programmer or a former C programmer used to type punning and your compiler is generous enough to just make it work even if it's undefined behavior, don't. Get your types straight. Don't rely on implicit conversions. and avoid narrowing conversions by at initialization time, for example, by always using curly braces, except with vector and initializer lists and so on. But that's a topic I dare not to, it's something we cannot fix. If you really want conversion, make it explicit, so you actually have to spell out the type that you want to convert to. Especially, I usually tell you avoid conversion operators except for explicit operator bool if you want to use a type that you can check for, let's say, being okay or not okay in an if statement easily. Do not perform arithmetic on promoting types. Well, I have a replacement library doing so by using enum class types and operator overloading, which is almost perfect, let's say, doing all the stuff that you might want to do without promotion, without implicit conversions. The only thing that you cannot do with it is indexing, because we cannot retrofit the indexing operator to accept an enum instead of an integer or a size t. Use strong types and libraries. Don't use ints. And again, summary of some of the stuff that I provided. I still dream of an integer replacement library that also does overflow detection instead of just wrapping. I haven't done so because it's not trivial to do that correctly. Some compilers provide built-ins to do so, but again, it's a lot of tedious work and very easy to make mistakes. That's why I write test cases with my code. The other safe numerics library that have a little bit different design approach, a little bit more overhead, but provide better error detection mechanisms like safe numerics in Boost. And if you really hammer hardware hard and you don't want to use these bad macros, let's say the hardware vendors provide you, try to have to construct your register replacement with my Bitfield library. Summary. Use value types, pass by value, return by value. We have been trained so long to use pass by const reference. It can actually be a pessimization on our 64-bit machines. And very often, it's due to move semantics that are implicitly applied by the compiler. It might even be the better way of working with that, especially if the call side manipulates what the parameter variable. Return by value is a no-brainer. Don't accident, if you want to signal, okay, I didn't get a value, I've detected an error, then return an optional, which is also return by value. And within now, and if you're not using C++23 yet, use another optional library instead of standard optional, which is deliberately crippled, and I have let's say, I have some idea why it's deliberately crippled, but unfortunately I wasn't in the room when that standard optional got torn out the ability to have optional references, which I would like to re-establish again. So, anybody here in the room has missed optional of references? A few, so please help me fight. No legacy loops. Consequent use and design of manager types, which I didn't explain today, but look for my talk on that. Treat compiler warnings as errors, use guts, use sanitize, and most important, have good unit tests. All the guidelines, even the MISRA guidelines who sound very stringent, have escape hatches. You might, let's say, for implementing optional reference, I might want to use a pointer. But that would be encapsulated and never leak the abstraction. And that's the important thing. For building powerful stuff, you might need to violate what I've just said, but you violate it in a way that your users of your code are not subject to have the same problems that you might get. So encapsulation of the, let's say, the dangerous, vulnerable code is important. And Find and use appropriate libraries and give feedback to the authors if they are insufficient. It's at least you can recognize that something works. And especially if a library has a good unit test coverage, it might easily just work and nobody knows that it's actually used. I had a time when in the late 90s when we created, let's say, web stuff for banks, where safety, security, and anything was important, and this was especially resilience. And I'm running out of, not out of battery, but out of screen. And our customers actually canceled maintenance contracts because our heavily unit tested code base was just working. It was good for the software, but bad for business. So, I'm done for today. Happy to take questions, ask me anything. Go take the stuff and please speak slowly. I'm a little bit hearing impaired.